All right, so the late selection filter models emerged to try and explain those circumstances where maybe it looked like post-attentive processing was the more accurate definition. So here we have a picture on the screen. Hopefully you saw it on the end of the last video and now you're seeing it again and hopefully you're trying to figure out what it is. So the premise in a late selection filter model is that attention is going to be focused after recognition is complete. So I picked this picture in particular, and if you already know what it is, or you figured it out, I think you can all agree that how are you supposed to figure out what the thing is in order to recognize it if you don't pay attention to it? Right? Like you have to look at that picture in order to figure out what you're looking at. And so I'm already, you can tell, a little biased against the late selection filter models. Now, if I give you a little bit more detail and you see these feet in the picture, it almost, if you hadn't figured out what that picture was prior, the addition of the feet probably completely cleared it up. You're like, oh, because before you saw the feet, you don't know what the size is. If you didn't know what this was, you're like, I don't know. It could be Swiss cheese. It could be, well, I don't know. Swiss cheese isn't usually white. It could be something really small. Maybe it's bubbles. Maybe it's something, you don't know what it is. You have no context to figure out what it is. Adding the feet, now you can go, okay, I know what the context size is. Okay, this looks like holes in ice. Okay. It's hard to imagine that you could go through that process without having focused attention onto it, isn't it? But the late selection filter model does acknowledge that there is some preconscious processing that occurs, but they say that it's happening outside of attention, and that it doesn't really count as a filter. So let me give you an example of what they're talking about. So they use these things that are called semantic priming studies. So to start off with, they show you pairs of words. So you've got doctor and nurse in this particular case of a pair of words. All right, so we've got pairs of words, and there's usually a list of them. So we've got pairs of words, and your job as the participant is going to be to decide whether the second word is a real word. So in this case, nurse is a real word, so okay. In this case, king and queen, the second word is not a real word, right? So we're going to have to look at these second words and see whether they are real or like a misspelling. Here we have salt and tree. It turns out that recognition is faster of the second word and whether that second word is a real word when the words are related. So you would recognize that queen is a non-word faster when it's paired with king than if it had been paired with nurse or if it had been paired with salt. The presence of a very um, semantically similar, right, or semantically related word like king and queen, and then recognizing that queen is spelled incorrectly, that's going to happen a lot faster when they're semantically related. All right. Even when you backwardly mask the stimuli, so we had the words salt and tree. A backward mask would be if we made the first word either disappear or we made it fuzzy or out of focus, something like that. That's a backward mask. So even when they're backward masked, if they are semantically related, will be faster than if they are not semantically related. Like salt and tree were not semantically related. If we had king get backward masked and we had salt get backward masked, we'd still be faster at recognizing that queen is not a word than we would be at recognizing that tree is not a word because tree and salt are not semantically related. So all of this is all a way of illustrating that priming you with the first word, right? So that you're already in this train of thought. Like doctor, nurse, closely related. When I saw the word doctor, I'm already thinking in this train of thought that would include like the semantic net, this you know, this neural network that would include nurse naturally anyway. And so I'm already thinking about it. So I'm going to be faster at recognizing word non-word if it's semantically related. And so this late selection filter model does acknowledge that if you're already thinking along that line, then you might experience what appears to be preconscious processing, and that's because you were already thinking in the correct way. Um, Now let's hop quickly out of filter models and talk about capacity models. Models that acknowledge that every task requires some effort. Every task reduces capacity that's left over for other tasks, and that we can use secondary tasks to estimate the amount of cognitive effort that a primary task takes. So if you're paying attention to one thing, the primary task, in my diagram here, it's in blue. So you've got a primary task that you're doing. You're going along doing your primary task. And then there's a switch of some sort where you need to complete a secondary task. And these can vary. Different researchers have done different kinds of things. The primary task might be doing a visual search for um, circles that contain a plus sign in a field of circles that do not. So you're busily you're searching for your circled plus signs, and then if you hear a tone, you're supposed to rapidly push the letter L on the keyboard. So that's your secondary task. So you're busily doing the thing that you're supposed to be doing, and then periodically, but you got to be like attending. You got to be dividing some amount of your attention to be listening for that tone that you're supposed to respond to, right? So the diagram kind of gives the impression that you're shifting um, like really dramatically between the primary task and the secondary task, but the secondary task is normally something that's sort of overlaying, that you have to pay attention to and decide whether it's time to respond or not. And it could be a button push. It could be, you know, you're you may have to stop what you're doing and solve a math problem and then go back to what you were doing. It could be, they've taken a lot of different forms in the research. So there's lots of different types of secondary tasks and switching that might occur. The key thing is the time it takes to respond to the secondary task gives us some kind of insight into how much cognitive effort is devoted to the first task. Right? So if you're searching for circles with plus signs in them and you very rapidly and very consistently, you're able to push the button to acknowledge that you heard the tone, we're going to conclude that searching for pluses is not a very cognitively effortful task. If on the other hand, there's a long delay and a consistently long delay, or maybe sometimes it takes you longer to respond than other times. That would give us some insight into how much cognitive effort it takes at the moment. Maybe it accumulates so that as the primary task is going on, you get slower and slower at responding to the secondary task, right? That would indicate that this primary task is difficult and that it really starts to wear you out. So there's different implications, but the key thing is we want to emphasize that we use that secondary task to give us insight into how much conscious attention is being placed on that first task. So what about automatic processing under the capacity model? In this model, there are certain kinds of information that it would be automatically processed, and these would be stimuli that it takes very little effort to process. You can do this unconsciously. Some examples: certain kinds of pattern recognition would be an example of, and not all patterns can be recognized without any effort, but some patterns can be. Like, for example, we talked about this with face recognition, that recognizing that it's a face, recognizing the age, old versus young, not drilling it down to what age they are, but old versus young, for example, or male versus female. This kind of pattern recognition happens automatically and with very little effort, usually unconsciously. A person doesn't say to themselves, "Let me look at this face and judge its age roughly and judge its sex roughly." That's not what we're saying. It's just something that happens automatically, doesn't take any effort. It doesn't require you to consciously try to do it. So those kinds of pattern recognitions with regard to face. There are other kinds of patterns like subitizing. That's another pattern that happens really automatically. So small numbers, you can quantify them very easily and unconsciously, very little effort. I'm trying to think of other good patterns that are good examples. Car just the vague shape of a car. Generally, a good idea of those kinds of stimuli that can patterns that can be recognized with little effort are those kinds of things that people can like sketch with very few lines and you know what they're trying to draw. Like if it takes more lines or more detail for you to figure out, that's probably not the kind of pattern that you could recognize without effort or without conscious awareness. But those kinds that can just be like hinted at with a few little lines and you know what the artist is going for, that's the kind of pattern recognition that you can do automatically. Language processing. If you've ever reflected on your own speech in particular, as you're trying to put words together into coherent sentences and things, sometimes you have to amaze yourself sometimes because you're like, how am I saying these words? And I'm not planning them. They're just coming out of my mouth, already conjugated, already strung together. How is that happening? Probably just like with visual illusions, those times that our visual system makes a mistake, the times that our language system makes a mistake is when it really attracts our attention. When you make a spoonerism and you mix up the first letters of two words and you're like, oh, that's funny. Why did I say that? Or you start stammering and you normally don't have a stutter, but you're sort of stammering. And a lot of times it can be because of what we call response competition, where two words could be used in this position and your brain's trying to decide which one to use. That can cause some stammering to happen, and you may stop for a second and say, "Why was I struggling so hard on that? Why did that trip me up?" So errors oftentimes are what cause our attention to be pulled and make us reflect on our own language. Most of the time, you don't have to think about it. You can just let it go, and for some reason, some magical reason about how our brains are designed, we can process our output virtually effortlessly. And then, usually, if you're talking to somebody or reading something that is well enough written, you can usually process incoming information with minimal effort. Sometimes people don't give you enough details as they're speaking, and you have to ask a bunch of questions to figure out what the heck they're talking about. um, I mean, that's a fact that happens. So it's not always smooth, and sometimes it has to do with, joining a person with their thoughts already in progress and you're like, what are you talking about? And you realize they were already like three sentences into the conversation before they started saying anything out loud, and that makes it really effortful for us to try and figure out what they're talking about. But in an average back and forth conversation, usually we don't struggle to figure out why they use the word rose, because in this context you know that they're talking about a flower, or in that context you know that they meant that somebody stood up, or you knew that they were talking about a color, or you know what I mean, like the word rose. You don't, even though it's a homophone and it can be used in lots of different contexts, you know from context that they don't mean that it's a person propelling a boat with an oar. That they actually mean, here's this flower I'm giving you, right? So you don't usually have to expend much conscious effort to understand language. So hopefully I made that case really clear for you. Now, there's a particular task that was developed back in the 50s by somebody named Stroop, and you may have seen this task in the past. Here we have what's called a congruent case of the Stroop design, where you have the word blue written in blue ink, the word brown written in brown ink, white and white, and so on. And if you go ahead and look at them, you get kind of familiarized with what colors are going to show up on the next stage of the task. And generally, if I were to ask you to read these, tell me the ink that these words are written in, you'll do it very quickly. And it's partly because you can recognize the ink, but also because you can just read the words out loud, and that's going to satisfy the task. And I don't know whether you're reading the word out loud or you're saying the ink. I don't care. You said blue when you were supposed to say blue. That's what matters. Where it gets tricky is in the Stroop condition, where now we have the same words, but now they're in incongruent ink. So now the word green is written in brown ink, and the word pink is written in white ink, and so on through that. And your job is still to name the ink. So you're supposed to say brown, white, purple, blue, orange, red, pink, gray, black, green. This tends to take a little longer for us because we get what's called interference between our unconscious automatic language processing, where we want to just read the word, and then the task that we've been given, which is naming the ink. So you actually have to you have to actively inhibit your tendency to want to read those words so that you can name the ink. Uh, Gosh, I think it was probably 20 years ago because it was before there were things like social media where things could just be memes. It was the kind of thing where people would pass it around as emails back in the olden days. And somebody was passing this around and saying, only really smart people can name the color of the ink fast. All of us dumb pedestrian people, we will be slower because, we're dumb. That's completely incorrect. Completely incorrect. We slow down when naming the ink in this case because we can read. Like that's a sophisticated development, right? It's not that you're dumb, it's that you can read. So yeah, naming the color of ink in this condition, the Stroop task reveals to us how automatic language processing is. Um, your position in space. Now I mentioned earlier, whether you're upright or upside down. That was an early Wilhelm Wundt study where they tried to have people tilted, and then later on into the like 40s they designed other researchers designed these chairs that they could strap you into, that wouldn't really feel super like you were straining against the straps as you were turning in different directions relative to the floor. um, so they really were trying to figure out how well people actually can process their position in space. And what no matter what they've tried to do, what they've figured out is people know whether they're upside down or not. People know whether they're horizontal or not. They know where they are in space. They I've done this with my students in class, and students will oftentimes say, "I have no idea which direction north is. I don't know. I had to go upstairs that twisted, and I had to walk down hallways with no windows in it. I don't know where I am now." And I'll just be like, just guess. Just guess, point north. And I won't even admit how many years I've been doing this demonstration, but I'll just say decades that I've been doing this. I've had maybe 5 students altogether that have pointed in the wrong hemisphere, like directly pointing south. Everybody's pointing somewhere between, northwest and southeast. They're sort of, sorry, northeast. I was getting a little, uh, what do you call that, compass problem myself. So yeah, between the northwest and the northeast, that region is where people tend to be, even though they insist I have no idea where I am. I've twisted and turned too many times in this building and haven't seen out a window, and I don't know where the sun is, and I don't know where's the freeway. They're mentally trying to come up with little heuristics to hang their hats on, and I force them just pick, and they tend to pick more right than wrong. Let's put it that way. They're not perfect, but they do know where they are relative to the compass, and at least vaguely. Um, that's because if you let it go and you stop thinking these inhibitory thoughts, your brain actually has been tracking your position in space. It's done unconsciously for you. They've actually, in the past 5 years, researchers have discovered that the same kind of mechanism that's in a bird's brain that helps them to migrate and know where they're hatching, their breeding grounds are and where their winter grounds are and stuff. Those exact same kinds of things are in our brains. We also have this unconscious natural ability. If we were forced, we could probably, if we trusted our gut, we could walk in the vague direction that we're trying to go. I don't want to test that out. Don't make me walk, but we'd at least vaguely be going where we're planning to go. The other thing is the passage of time, and I'll just give you this example to really drive this idea home. If you've ever woken up prior to your alarm going off, that's because your brain is so good at processing the passage of time that it does it while you're asleep. It's such an unconscious process that you don't even have to be awake. Your brain knows that you want to be getting up at X time, and it tracks the passage of that amount of time. It unfortunately tends to be a little early when it wakes you up early. It annoys me that it'll wake me up like 20 minutes before my alarm was going to go off. And it's like, nah, see, if you had woken me up like an hour and a half ahead, it would be worth going to sleep again. 20 minutes, I'm just going to be drowsy when the alarm goes off. So I guess I might as well get up. And I don't like that. But it does, it like has this really good, they've done research on people in windowless rooms with no clocks, and they ask, they'll leave them there for variable amount of times, and they'll ask them how much time has passed, and people are usually accurate within 5 minutes per hour. That's pretty good. Like, that's pretty accurate, and they have no cues. They're just trying to figure it out. They have no way of tracking it. They're just trying to figure it out. So passage of time is unconscious for sure. So the automatic processes typically are attracted by the characteristics of the stimulus, just like the selection theories had said. Another factor that can contribute to automatic processing is overlearning. If you practice something beyond the point of knowing it and to the point where you can't not know it, that's what we call overlearning. And if you can practice like that, you can make that task into something that you can do without any cognitive effort at all. You can actually free up your cognitive capacity to do something else while doing what had been an effortful task in the beginning. I'll give you a really simple example: walking. I have grandchildren, so I get to watch it all over again because it's been, a while since I had babies, obviously, 5 grandkids. So watching the grandkids do it, walking is super effortful when you're learning, right? It's like any slight movement and you fall down. But then once you practice it enough, now you can walk and you can talk. You can walk and you can text. You can walk and you can think other thoughts. I mean, you don't have to think about walking anymore. Occasionally you're out someplace with uneven ground or walking on a jetty where there's a bunch of rocks or something. Now all of a sudden it gets effortful again. But if you're walking on a level surface like a toddler is doing when they're learning to walk, you don't have to exert any cognitive capacity to the act of walking. Similarly, overlearning, now as an adult, you might have the experience of having overlearned driving. So you may have practiced to the point of being able to do more than one thing while driving, right? So what had been a really super effortful task where you really had to think about it in order to complete it, if you've got any practice under your belt with your driving, you've probably gotten overconfident a little bit and you're able to eat or put on your makeup or mess with your phone or other things that you didn't do when you were learning how to drive, but you've overlearned that task. And so now you have cognitive capacity to devote to other things. Um, so those are my examples of that. Let's go ahead and stop here and we'll talk about some of the problems with automaticity.